Hello everyone, my name is Jiaming. Today I will present chemical solubility prediction using machine learning project for data analytics 5030 course. First, I want to talk a little bit about why I want to predict solubility of chemicals. The main reason is um, I want to predict the solubility for ionic liquids and deputative solvents. These two types of organic solvents are attractive for researchers. However, there are millions of possible combinations of different cations and anions to form ionic liquids and deputative solvents. Therefore, to screen out the best performance combination of millions of possibilities, that will cause forever to accomplish. Therefore, I want to use machine learning to decrease the computational cost for making such a prediction. The goal is to predict the chemical solubility in water by only using their structure as input. Based on these structures, we can calculate the number of different atoms. And based on these different types of atoms, we can then calculate the hydrogen bond acceptor numbers, um, the number of heavy atoms, the molar mass of uh, the molecule, or the polar area at the surface of these molecules, and so on. After that, we can feed these quantitative data into machine learning algorithms, and these algorithms can predict uh, the solubility of new molecules from the test data set. The data from the beginning I have contains only a little bit more than 1,000 structures, and the experimental solubility and the calculated solubility from the literature. So there are only 3 columns or 4 columns, but there's nothing about the features. How do I find out the features? So I use the PUG REST API. This is provided by PubChem. I use from JSON to call the structure of different atoms. Then PubChem can return a JSON file um, for this specific atom, and I use from JSON to process this JSON file and save it all the features of all molecules into a table. This is a brief code demonstration for data collection. There are 4 red rectangles. The first one is tell us that I just loop through all the names of chemical structures, and the second one is I made the API URL for each molecule. The third one is to send the query to the API server and process the return data. And the final red rectangle indicates that I use rbind to combine each um, to combine all features of each molecule into a large table called DF. After we collected data from the website, we can see that there are 20 different features, and the first 3 features are just identification of each molecule. From 4 to 20, these are the chemical or physical features that we are interested in. The red figure shows the histogram of these features um, to uh, take a broad overlook of the data distribution of each feature. Among these features that we can see, there are several graphs for example, the atom caret DEF, the first row, second column, is full of data. That means there's only one value in this column. This also happened to the covalent unit and isotope atom. Therefore, we need to drop these three columns in the future data cleaning process. After drop that three columns, I then rescale the whole data set to using min-max normalization. Specifically for molar mass, you can see in the previous slide, it is widely distributed. Therefore, I applied the logarithm rescale to this column specifically. Actually, I also try to use logarithm, apply logarithm to the polar area as well as complexity columns. However, these two columns contain zeros, and so it's impossible to take a logarithm to zero because that's going to be negative infinity. One trick to use is to replace zero with very minor small volume so that I can do that without any error, but that doesn't matter in my perspective, since molar mass, complexity, polar area, these all three are a little bit has a little bit collinearity. For the new features, you can see the top left corner. I add two features. One called H acceptor ratio. That's just the H acceptor divided by molar mass, and the H donor ratio. That's the number of H donor divided by molar mass. These two ratios can better describe how many H acceptor or H donor in each molecule per molar mass. And the brand new feature I developed is called C other. That's the ratio of the number of carbon atoms divided by the number of oxygen, sulfide, phosphorus, and nitrogen atoms. The more atoms I said later, the more possible that these molecules are soluble in water. After we finish our data preparation, of course, I didn't include all the data preparation process because that will be tedious and time consuming. The three models, the three machine learning models I'm going to use for this solubility prediction is are model tree, linear regression, and artificial neural networks. The reason I use these three is first because this is a regression problem. So model tree, linear regression, and ANN are capable of them. Furthermore, as the knowledge from the chemistry, these features could possibly have some linear or maybe parabola relationship to the solubility. Therefore, using linear regression could be appropriate, and also for the model tree, because broadly we can classify the chemicals into soluble and insoluble. Also, for example, for the molar mass, we can classify if the molar mass is smaller than 100 Dalton, smaller than 500 Dalton, or smaller than or larger than 1 kilo Dalton. And also in each node, we can apply the linear regression, which will be promising as for me. Also for the ANN, because ANN is capable of both classification and linear regression problems. Also, we are not clearly understand what's the relationship of these chemical and physical features as to determine the solubility. Therefore, the ANN is very fit to our thought because we don't know what's the relationship between all the features. ANN can help us to predict it. Therefore, I use these three models. On this slide, I will talk a little bit about how did I train the model, test the model, and collect the accuracy of the model. On the left-hand side, the first line, I set the seed to 0. For the second line, I use fit function. The fit function is from our minor package, which using NNet artificial neural network algorithms. So I use fit function to set the solubility as our target, use all the features from the training sample as input features, use MLPE as our model, use 16 number of nodes and 0.1 as decay and 500 max iteration. And then I predict the target using the test sample and I save the performance. The performance is quantified by MAE, RMSE, and RSQ, and I save all these errors for each molecule into a large table called overall error. The overall error is look like the red bottom table here. So it has 4 columns. The first column is the model name. The other columns are the errors. On this slide, I want to show you how did I do the hyperparameter tuning for artificial neural network with tenfold cross-validation method. The left-hand side is the code. I don't want to dive too deep into it. We can just see the right-hand side. So this is the graph shows the sum of MAE and RMSE as a function of number of hidden nodes. So when the number of nodes is 6, the model showed the best performance, and followed by the 8 nodes and 13 nodes. Therefore, we may want to use the 6 nodes as our best ANN model for the solubility prediction. For the bagging example, I use the bag function from car-et package and use the C-tree bag and NNet bag algorithms come along with this package for bagging example prediction. And for this page, I listed the top 5 models with smallest error. That the error defined here is the sum of MAE and RMSE. The best model is artificial neural network with 16 nodes using PLME argument, using tenfold cross-validation, feed all the features in the dataset, followed by the NM with the default number of nodes. And the third place and fourth place are from model tree. This is pretty surprised. For our solubility prediction, the model tree performs really well, compatible to artificial neural network. We all know that ANN requires much more time to compile compared to the model tree. Therefore, if we have a large data set with limited computational power, we could use the model tree for the solubility prediction. After evaluate the model, the performance on the test side of all the models, I then predict dopamine and adrenaline solubility in water. These two chemicals are out of the data set we have, and I put the structure of these two molecules here. You can see the structures are very, very similar, but if you look at the data downside, for the experimental solubility data for dopamine is 600 grams per liter, and for adrenaline that's only 0.18 grams. So these similar structure, but 154 difference of the solubility would give us models a lot of trouble. Also, our models has relatively poor performance on both of um, the molecules. You can see in bagging for dopamine is a little bit less than 3,000, and model tree is a little bit smaller than 4,000. For adrenaline, in bagging has 120-ish grams per liter, and the model tree is 600, more than 600 grams per liter. Meanwhile, the AN with 16 nodes has the closest solubility prediction to the experimental uh, data. Therefore, all of our model perform poorly on these two structures. At the end, I want to sum everything up. First, I want to say is the performance of our models are pretty good compared to the literature. So the error of literature, the mean absolute error and root mean square error are 0.69 and 0.91. Our model decreased to 0.39 and 0.52. Also, the solubility calculated in this project is actually the log 10 of the actual solubility measured in experiments. Therefore, the actual improvements on the solubility prediction is much larger than these four values can present. The second point, the second thing is the model tree and artificial neural network perform pretty good and almost the same for solubility prediction, especially for model tree because it doesn't require too much adjustment. On the other hand, ANN needs to find the best number of nodes to considering both underfitting and overfitting. Also, the training time for ANN is way too much than model tree. Therefore, in the future, if I have a chance, I would like to mainly focus on model tree and with an improved data set for solubility prediction. The third thing is feature engineering improve the model performance a bit. If you take a look at my R notebook, the data set with engineered features has a better performance, maybe 10% improvement than the data set without these three features. Also, if you remember from the last page, from the last slide, the dopamine and adrenaline have very, very similar structure but totally different in solubility, which is the impact of amine group on the end of the structure. Therefore, some features to describe this structure differences are necessary for a better model for the solubility prediction. Therefore, if I have a chance, I would like to calculate how many amine group are in the end of the structure, and maybe some other groups like OH groups, NO2 groups, etc. So this is a very important feature that we need to consider for a better model. The fourth thing is always keep in mind is the garbage in, garbage out rule. There are a lot of data outside on the online. Also, why I want to mention this is because all the data I use to calculate the solubility is the theoretical data instead of the experimental data. The reason people don't use experimental data is, one, there are too many chemicals available, and two, the labor cost is too high. So if we could use experimental data instead of the computational data, the model will be much more trustable. And the final point is the large error on the dopamine and adrenaline solubility. This has many possibilities. As I mentioned, maybe the missing features, for example, the amine group, maybe the small training size, because the whole data set only contains little more than 1,000 observations. Maybe we use 10,000, 50,000. The model will be performed much better. And also, this large variance could be caused by overfitting, but because the performance on the test set is relatively good. Also, the k-fold cross validation is also performed during the training process. Therefore, it could be, but it's not going to be the main reason for the large variance of this dopamine and adrenaline solubilities prediction. All right, thank you for listening, and thank you so much for the whole semester. I really learned a lot about the machine learning, and I hope I can read that book carefully throughout and again to catch up everything, because I feel like I missed so many details underlies these packages, because using functions are easy, but understand what underlies them are going to cause a lot of efforts. Again, thank you for listening.